Hi everybody, welcome to the presentation. Standing in for Zubair Sheikh, who couldn't be here today, but hopefully he'll be able to give a talk in the future to be worth to listen to. My colleague with me is Meyer. Dennis will take over halfway through this presentation to walk you through the Hadoop parts. So what I'm going to talk about today is what is real-time bidding in the context of online advertising. I'm going to have a look at the real-time bidding exchange architecture, and then we'll continue on to look at the data handling in Hadoop. So what is real-time bidding? Well, we're all familiar for going onto the internet and getting some nice content. Of course, it's all free for us to look at, mostly. But someone has to get paid for delivering that content. And this is mostly paid for by advertising today. And traditionally, advertising is done with upfront agreements between publishers and advertisers. So this means, in this case here, we've a banner ad displayed at the top of Verizon. Verizon might have come along and said, we want to buy 100,000 impressions of this banner on his webpage per day for the next month. That's very inflexible. It doesn't really help if you only want a few hundred ads displayed. You don't have sort of budgets that Verizon might have. And as well for the publisher, a day later the publisher might find out that some advertiser wanted to actually pay a lot more than what Verizon did to get their ad displayed there. But if you're locked into an upfront agreement, that's too bad. So this is where real-time bidding comes in. Real-time bidding is the buying and selling of those impressions in real time while your page is loading. So we have two players in the real-time bidding architecture. We have the SSP, or supply-side platform, on the left-hand side. They represent the publishers. So each time your browser is making a request to the publisher's webpage, the SSP sets up an auction and invites DSPs, or demand-side partners, to take part in the auction, and those demand-side partners represent the advertisers who want their ads displayed on your webpage. If we take a look at the different components involved in actually doing the workflow, it starts off when your web browser makes a request to the publisher's website. So we download the HTML there, and inside that HTML there is a request which gets fired off to an ad server. This ad server does some decisioning. Part of that is it decides whether this publisher wants real-time bidding on their web page or not. If they do want real-time bidding, then the request gets forwarded on to the real-time bidding exchange. This is the part we do in Erlang. The real-time bidding exchange then gets to decide, well, which DSPs should we have in this auction, and it will build and send HTTP requests with JSON encoded data in that to the DSPs. The DSPs will hopefully respond within a certain time limit that's been predefined ahead. And when they respond back, they're giving back a bid price, which is how much they will pay to get that ad displayed on your web page, and also a JavaScript snippet, which represents the JavaScript that they want put onto the web page. So once a winner gets selected, the request goes back via the ad server and then off to the web browser. And that JavaScript snippet at that point then fires off a request to the advertiser content delivery network, and the ad gets displayed on your web page. So we'll have a little look about the real-time bidding exchange, and what the architecture of it looks like. So it starts off when the ad server forwards this request to the real-time bidding exchange. The request is actually a thrift encoded message, and it's sent over a 0MQ interface to a 0MQ endpoint on that real-time bidding exchange. 0MQ has been very flexible for us, so as well as connecting one ad server to the exchange, we can connect multiple ad servers. And in addition to that, we can add in as many real-time bidding exchanges as we like and connect those back to the ad servers. What it means for us in practice is We can add or remove ad servers or real-time bidding exchanges. The ZRMQ layer then is doing the router dealer pattern, and it's distributing the load equally across those real-time bidding exchanges. So we can take any one of those out of service at any time. So once the request has got to the ZRMQ process, it spawns another Erlang process for the auction. We don't use OTP behaviors for this. We're just using proplib to spawn the process. We do use OTP everywhere for long-lived processes, but auction processes should be very quick and only living for a few milliseconds. And if something did go wrong with an auction process, there isn't really time to respawn it and try sending another request again. But that auction process is going to look at the request which comes in. It looks at things like what IP address was it from, and it can map that to a geolocation. It can map it, did it come from a web page that had secure content only on it. And it could also look, maybe it didn't come from a desktop browser, maybe it came from a mobile app instead. So there's lots of different categories of information for it to look at, and then it must decide what campaign information maps what came in on that request. So all this campaign information is stored in ETS tables. We use these quite heavily with read concurrency set on them, so we can have lots and lots of different auction processes in the system, all concurrently accessing the campaign information ETS tables. This is how we actually get the data into the ETS tables. So the real-time bidding exchanges are the ones in the bottom here, but on the top left we have an Erlang config service. This Erlang config service takes configuration in the form of JSON documents and populates MySQL clusters with the JSON documents. So when a real-time bidding exchange node starts up, it has a hashing algorithm there to tell it which host out of the MySQL cluster should it connect to, because we want to have all these connections distributed evenly. And at startup, it will just read down all those JSON documents, decode them, and store them natively in the ETS tables. Periodically, it has to check, has there been any new config added to the database. So polling continually goes on onto the MySQL cluster there, while all these auctions are happening at the same time. So in addition to getting that sort of static information from MySQL database, we have a Couchbase cluster. This is being populated with information from the different DSPs that we will connect to. So our auction process does have to connect to a Couchbase cluster. We found a nice application on GitHub, Erlang, and that implemented the binary protocol we needed to connect the Couchbase and make requests there. Once you've received all the configuration information and the user mapping information from Couchbase, then we need to decide who can actually take part in the auction. So some of the DSPs might be disabled for a certain period of time. Maybe there's some issue going on with them. Some of them might be throttled because they can only handle so many requests per second. Some of them might not be able to handle the requests because they don't handle secure ads. And then some DSPs maybe only handle ads for mobile applications. So there's a lot of different filtering and decision making has to be done to figure out which DSPs can be in that auction. So finally, we'd like to build an open RTB protocol message and send it over HTTP to the DSP itself. But to do that, we need a connection to the DSP. So we're using an application that holds for us pools of sockets towards each DSP. So each socket is looking after a long-lived HTTP connection. It's been a tricky part of the system to take care of. If DSPs are working normally, then the idea is you take the socket out of the pool, send a request, get the answer back, and then we can put the socket back into the pool for them to reuse. But if you get some DSPs that maybe had a bad deployment someday and maybe stop working as they expect, they might start closing all these sockets on you, and then that leaves you with lots of time-weighted connections on your system. So looking after these pools and deciding how many sockets you want per DSP in there is something quite important to look after. And then finally, we get the responses back from DSPs. The responses go into the auctions, but we still have lots of filtering to do on some advertisers might be whitelisted, some are blacklisted. There might be buyers representing different advertisers, which can be whitelisted or blacklisted. DSPs can respond with maybe a deal ID, which is something they set up with the publisher, not really in our control, but that might give them a certain advantage with that particular publisher. So we have to take care of all these different events in the auction, and then we decide the winner and send it back to the ad server. So as well as the auction which goes on, this exchange has a nice user interface where we can connect to it, see that it's working, see it's got its configuration data and handling connections. We're exporting stats via SNMP. We also have FullSmart running, so we're exporting a lot more metrics to that there. So we use Grafana a lot for developing different dashboards. With Grafana we can look at, see how different DSPs are behaving, and we can see lots of different timers for the auction process. I think we time about 10 different sections of an auction process. So if we add new software or our configuration changes a lot, we can easily spot where are we spending more time, in which part of the auction we spend more time now compared to, say, last week. And one of the new additions to the system is creative scanning. So when DSPs do respond with their ad markup, as well as doing the auction on that, we're taking this ad markup, sending it off to a third party for scanning, for checking is it a really secure HTTPS, does it have malware, what kind of industry is the advertiser associated with. So that kind of scanning also influences the auction decisioning process as well. So we rolled this system out about 3 years ago in production with one DSP and maybe doing a few hundred requests per day. We've got up to it now where we're sending around 60 billion HTTP requests per day to all the DSPs that are there. On a single host that, I think what we've seen in maximum production is handling about 13,000 requests to DSPs per day. I don't know if that's a good number or a bad number, but it's not just one or two. I think we're quite pleased with, but I think we're still trying as much as we can to squeeze as much out of the system as we can. This kind of shows how a node does scale with the different requests. It's almost linear, but it's even tends to flatten out as we get towards the end. On this particular day, there were 12,000 requests sent to DSPs in a second. Each point here is the maximum CPU load on a 10-second interval. So it's quite interesting to look at. There's definitely a lot of white space around the line. So I think we've got quite good performance. At 8,000 requests per second, sometimes we're like 60% CPU load, and sometimes it's 70. It's problems like this that we're really dealing with every day, and trying to figure out why can we not do all the requests just at 60% CPU. But another thing we're quite pleased with is it's an IO-bound system where we're handling requests coming in, and we're doing a lot of waiting for requests coming back from DSPs. So actually being able to get our CPU up to the 70, 80, 90% range, it's something we find Erlang is really good for. If we look at a single request, I said this part of the system we're not using OTB behaviors for, but we do spawn not a lot of processes, but per request you can see the 0MQ message handler will spawn a request for the thrift request handler. That's just decoding the thrift message. Then it will delegate the auction to the auction process. And then the auction process fans out to DSP processes, which use these HTTP client processes. So it's a mixture of using processes for fault tolerance and also for fanning out the system to get it to work in parallel. This is just a quick demo. Don't worry if you can't read this writing. What it is, each blue dot is a process used in a single request. This is one single request. The processes are joined together by lines because there's links between the processes. And if we have a little bit better resolution, you'll be able to see process IDs against that. So typically at any instance, we would have hundreds of these auctions going on at any one time. And what we're trying to show here is, let's just get a picture in our imagination what hundreds of auction processes going on in the system would look like at any one time. This is just a little application called EarlGraph. You can get it off the AOL GitHub account. Just add it to your rebar config and start it up, and then you just point your web browser. You'll be able to see all the processes that are going on in your system. Don't try it when there's too many processes because it's D3.js force-directed graph, and the browser will have trouble rendering this once you get past a few thousand processes. So I'm going to hand over to Dennis at this point.
So my name is Meyer. I'm chief architect, especially on the data side. So as you've seen, we're working with mass data. 60 billion, you saw as a number. So in data handling, size matters, right? I think there's kind of a big difference between small amounts of data and big amount of data. So we've grown bigger and bigger, and the challenges are getting more complex. Especially when you're reaching a certain threshold, because you're entering a certain limit where not many people are working with, and it's getting a little bit of a beta touch sometimes. So what is big data? So we are talking about NoSQL. We are talking about NewSQL, which is more relational databases which are enhanced, like columnar data stores, like clustering, parallelization, linear scaling, case safety, eventual consistency, MapReduce, and more, right? So just to give you some metrics, what we are dealing with, 2 times 100 nodes, that's the size of our Hadoop clusters at the moment. That's our current setup. We've got 2 clusters, just of how our data centers are distributed. We are creating 2 terabytes. Excuse me. Hi? Okay. So we're upside down. Does it work? Yeah, perfect. Okay, so we're creating 2 terabytes an hour. So just as a fun fact, so we're writing log files out. So it's more or less it's compressed, but it could be if it was readable, just written out text. Fun fact, this would equal to 500 million pages. So it's a 50 kilometer high pile of paper. A4 or A4 paper. So everybody talks about terabytes, but doesn't know what it really is about. fix that once forever. Okay. Okay, now it should work. Okay, so we've got 20 terabytes stored in our data store in the background. So that's a reporting database. So that's 20 terabyte of data. So that's kind of a paper pile which would reach from Berlin to Stuttgart. So how do we enter kind of the data world in that architecture that you saw already? So that's kind of the same page that you saw before. And in here, we are simply hooking kind of into the ad server. So on the way back that we know who has won kind of the auction, we're giving back that information to a component which we call the log collector. In here we've got multiple different iterations in logging out the data. So there was different implementations, and we ended up writing our own because we had a lot of scalability issues. We're using Flume, and as we were logging out so many data, we were kind of pretty we were pretty unhappy with the performance, and we used a lot of resources that we didn't need to. So what we ended up with, we've written our own log collector that's written in Java based on Netty. What we're using is kind of, we're using ring buffers, so we don't allocate data multiple times. So that's maybe the contrary picture of immutable and respawning. So we're just allocating it once and reusing it, right? So everything which is coming in, we're simply using it once again, so we don't have any memory allocation. We're just reusing stuff, right? Recycling. Another thing that we are doing, and that's also important to the data, to one of the speakers before, we have talked about optimization on the database side, about blocks in databases. So we're using zero copy, so we don't kind of copy over data once from one point to another. And we've seen that this has been a big issue in a lot of logging frameworks, because sometimes you have to take a decision between low level and performance, or high levels, which is more stable and usable, more feature rich, and in here there's kind of a disconnect sometimes. So in here we have got the possibility to tune it kind of. Also a benefit is that you could also kind of contribute to maximize the TCP layer throughput. So also in here we saw a lot of issues where TCP buffer were limited, so we're not reaching kind of the real throughput on kind of the large scale networking issues. All of that is kind of a, from code line perspective, a small project. It's not as feature rich as, for example, Flume or whatever, or Kafka, but it's kind of pretty performant and has got a lot of throughput. What are we logging out really? So we're using a binary format. So binary has got the benefit that you got kind of a compressed format, and it's not eating up so much space as you're using kind of plain JSON, XML, or whatever format you're thinking of. It's supporting structural data, so arrays, trees, etc. It's using compression. It's kind of self-descriptive, which makes it really handy to work with. So if you're writing out a file, the first part of the file is a human-readable header. It's not only human-readable, but also machine-readable, so it's JSON. So this is a real-life example how kind of one of that headers look like, and after that it's kind of it's binary, right? So the rest of it is not human-readable. But that makes it really easy to handle those files, because we've got multiple different versions on the disk, and the machine can differ between the two, and a human can as well for debugging purposes. And there's another benefit that's not on the slide. You don't need to pre-compile it. So in comparison to Google protocol buffers, you don't need to pre-compile it. Also, it's used kind of in Hadoop pretty much, so it's kind of pretty chiming in. So partners in crime, Erlang and MapReduce. So I think you've seen in the slide that Erlang is producing a lot of data, and we're using kind of the scale out in the horizontal way to produce a lot of data. And what we're doing now here is that that we're using kind of MapReduce and Hadoop to process that data amount. So that's just out of Wikipedia, right? So what is MapReduce really? So it's a framework for processing parallelized problems, and I don't even want to continue. So we're talking about cluster and separating data and parallelizing stuff. So how does it really work out? Oh. Okay. So normally if you kind of look into some Hadoop tutorials, normally they talk about word count. So one of the problems that is normally kind of asked here is just take a book and count each and every word. How often does it kind of appear in here? And of course you need to count it as unique. So it's a complex problem. It's pretty suited for parallelization, so that's kind of really nice use case. So what is happening here is, the left-hand side you have the input file. Then there's the splitting. So that's how the data is fragmented into Hadoop. So on multiple different machines, you've got different data. So that's one line per box in here. Then there's the mapping happening. So the mapping is kind of the first processing step in here. So you've got a counter, and each and every word has got a count of 1. So it's pretty simple. So you're just kind of transforming the file to kind of a map. Then the shuffling happens. So in here, you're copying data across kind of different machines, right? So that's also a costly operation, because that's also kind of writing files. So in the original implementation, you were writing files on different machines. So there's a lot of data going on the network and also kind of persisted on disk, so kind of a read-write operation. And as you see in here, it's kind of ordered, so that kind of the same data ends up in the same machine, so you can process it, right? So in the next step, that's kind of the reduce, so MapReduce, right? So we're coming near to the end. In here, the reduce step is the real processing, right? Real processing is not really true, so you can kind of have business logic on the mapping and the reducing side. But in this case, we're having kind of it on the reduce side. So what we're doing is we're kind of simply summing up for getting kind of the overall number, right? So if you look at the bike, it's 3 bikes, it's simply summed up. And that's happening on all the boxes in parallel. Then we're sending it back to one central box, and we've got kind of the results file. The interesting thing here is that we're kind of maximizing I/O throughput, right? So if we're looking into the boxes, everything can run in parallel. And the better we kind of organize that, the better the throughput is. And that is also kind of up to parallel systems. So the better the different boxes work independently on their own, the better it is. If you've got a lot of network communication, right, the problem is kind of growing exponentially. So the more network communication you have, the worse it is, right? And in here you see kind of the shuffling, for example. That doesn't look that nice, right? But it's needed. So the second thing that we're using is kind of, we talked about the 20 terabyte in the database, right? So 20 terabytes is normally nothing that somebody has in its database. So we're using kind of Vertical, which is a column data store. Anybody of you using column data stores? A few. Okay, perfect. So those of you are familiar. For the rest of it, it's pretty simple. So just that's kind of a table example in here about some raw of data. So that's how it looked like if you just do a select star. In a traditional data store, we're talking about those blocks, right, which is written on disk. I don't want to go too down into database theory, but how it looks like on disk is, on a row store, you've got all the data kind of side by side, right? So if you've got a row, all that data resides next to each other inside one block in the file system at the end. And that makes it, of course, easy to read the complete record if you're just accessing the block. It's one read, one block read, and you got all the data. But normally what's happening is that we don't even read all of the data. So we could optimize kind of the block reads if kind of we would only have the data that we need in one block. And that's the real idea. So what we're doing is, instead of kind of writing it out all block by block, right, we're kind of only focusing on the columns. So one column is written out completely, then the next column is written out, and so on. And what's happening if we're kind of accessing the data, we have kind of, normally the magic is that we have kind of instead of using an index, we're having kind of sorted it on disk. And normally we're using compression so that it doesn't grow too big. And we're using kind of normally a smart indexing like binary search on top of that. And we're jumping into the data. So example, if you select for Germany, we know it's a third one. So we also know that chocolate is a third one, so that's Germany. And the third sales is also kind of 4,000. So depending on how many fields you read, the more selects you need to do. So if you just ask for what is kind of the preference for Germany on a product side, you just access those two columns. So it's a duplicate access, but it's reading a lot less blocks and it's more optimal on the accessing. So if you're talking about large data, it outweighs kind of the additional storage that you need to, because you have some duplication on the storage side. That's the downside of it. When we're talking about the aggregations inside Hadoop, so the pre-processing, the number crunching, all of that is done in MapReduce jobs. MapReduce jobs you can write them your own, like in Java normally, kind of that's the original idea. You can also do it in Python, and there has been a project we're also using was also running on not MapReduce, but on Hadoop, so they might have also used that, so you can hook in whatever language you want to, but you need to write it your own. And as you see, it was like always creating a map, creating a reduce phase. So what about a traditional relational database system? It's a select, count, whatever, do a join. So you guys are used to kind of SQL. If you want to write kind of a join on MapReduce, it's pretty complex. You need to do a lot of stuff, a lot of steps. Doing that your own, you don't want to, right? So there's kind of extraction script languages like Pick on top of it, which take part of that and is creating those MapReduce jobs for you. So it's a scripting language, and the outcome of it is a MapReduce job, a native MapReduce job. Pick is kind of data stream oriented. Here's a small example on it. I don't want to go into the details, just that you got a kind of impression how it looks like. And it is kind of SQL-ish, right? But it's the other way around, it's kind of data stream related. There's also other frameworks like Hive, who create MapReduce jobs, who is using SQL, right? We're also using that, but 99% or 95% using Pig. That's the architecture of our reporting systems. On the left-hand side, you see the ad servers, the log collectors we talked of, that ends up in Hadoop. In Hadoop, we're using Pig. The Pig results are kind of ending up in S3 buckets, so we are in AWS. So those results can also be easily consumed by our clients. So if one of our clients asks for dedicated data set, aggregated in a certain way, we can do it, and you can simply grab it on an S3 interface. That makes it pretty simple, because it's a simple HTTP access to the files with all of the control that we have on it. For our internal reporting, which is on the left lower hand side, that is kind of using Vertica. The dimensional data, that's kind of the campaign configuration data. It's the strings, what's the campaign name, what's the advertisement name. So we are logging out only integers, only kind of numbers for optimization. So we need to join that information, so that's happening in here. So what's next? We're kind of looking into getting more into the Lambda architecture. We already have some real-time system, which we have built our own. They are not that flexible as we want to. So we're looking into getting kind of a little bit more speedy things going on. Also, Spark overcomes some of the limitations on writing out files on disk and reading them again. So it's streaming. There's also some effort done in Hadoop itself, which is kind of the Yarn framework. So you can leverage streaming a little bit better, so that everything, not all the exchange data between nodes need to hit disk directly. Also, Spark is using kind of Scala. It's going a little bit more to the direction of Erlang. Also, kind of Akka should be familiar with most of you guys. So it's kind of a carbon copy on the Scala side of Erlang. And they also say that they used Erlang as a template, so it's looking pretty much the same. And you know, we're hiring, so we're doing not only Erlang, so we're using Java, C++, Erlang. We're in the advantage that we're kind of in the advertising business. We're dealing with huge data, and we're using a lot of new technologies because we need to, right? We need to keep pace with the industry. We are not a financial company. We need to have a lot of limitations. Or no, we are not giving your data away. So if that question is coming, so we're more restrictive than you think of in that sense. But on the data side, we're not. So we're using a lot of fancy frameworks: Hazelcast, Redis, Couchbase. All of that is somewhere in our architecture. And we have a lot of hirings kind of on all the different technologies, also in different places: Germany, Dublin, US, whatever. Any questions?
Go on.
Thank you very much.
You can have questions, right? Yes, you're
You use Thrift and Avro. Why do you use both of them?
So indeed, we're not using kind of Thrift in here. Not on the logging side, so that's kind of a plain TCP message, whereas the payload already is Avro compressed. So if you're, when the ad server is getting the information back, it's already kind of creating the Avro format as binary, and then we're kind of sending that over the wire using a TCP message with the header having got some meta information that we know where it ends up.
That I understood, but at some point you have the 0MQ process creating Thrift as a Thrift listener. And so that's because you're using Thrift to your outside entities. That's a outside interface. Is that what you're doing?
So you're talking about the protocol between the ad server and the selection engine. That's decoupled because the ad server itself getting in the request, doing the parsing magic, and then transforming it into some already machine-readable protocol, and that is kind of the part that you've been referring to. So that's not happening on the logging side, but on two different machines, which are kind of handling different parts of the load. So it's kind of two tiers.
I understand, but they're both serialization mechanisms, right? So why did you decide to use different ones?
Because there's different needs. So one doesn't need to get logged out to disk, right? So if you're talking about Avro, there's some compression and data handling needed. That would be overhead if it's just kind of one machine already has it as an object in memory. It wouldn't need the serialization magic. So you would get around that that processing, right? Yeah.
Last question.
On the handling of the ads getting kind of the DSPs sending messages back, you have time constraints. Are those kind of handled by using the soft real-time in Erlang, or do you have actual real hard limits there?
We're using the soft real-time, so we're just we're using the timers we get from Erlang. So built-in timer wheel.
So how long are those times?
Those times can be configured. So different publishers might have different needs. We're talking figures in milliseconds, and for some people they're small milliseconds, and other people they could be hundreds of milliseconds. So it's entirely configurable, and it depends on the customer using it what they want to get from the system as well.
Okay, thank you very much, both of you.